Thank you very much. I want to take a few minutes and welcome you to the Spring 2019 Wulff Lecture. So thank you for joining us here this afternoon. If we haven't met, my name is Chris Hsu, and I'm the head of Course 3, the Department of Material Science and Engineering here at MIT. And on behalf of everyone in the department, I want to thank you for coming out here this afternoon to listen to the Wulff Lecture. This is a really special event for this department. We hold these lectures from time to time, usually annually, in order to celebrate our field and one of its true pioneers, John Wulff. And if you don't know John Wulff, here he is. John Wulff was a professor in our department in Course 3 from 1937 until his retirement in 1973. And I kind of like that symmetry, 37 to 73, because if I try to live up to that, I get to retire next year. So he had a long and illustrious career in the department, and he had a lot of amazing accomplishments that stand out. But among those accomplishments, the ones that stand out the most pertain to teaching and communication. He was a professor, and he developed 3091. Can I have a show of hands? How many people in the room know something about 3091? So it's virtually unanimous. So 3091 is a legendary introductory freshman class that what it does is it takes a whole lot of 18-year-olds and shows them what material science and engineering looks like for the first time. And he developed that class for the department back in 1968. And it's still a popular option to this day. And it's a popular option because he started it on the right foot. He was a riveting lecturer. He loved to teach. And every one of his lectures was like a choreographed performance. And in fact, if you enjoyed this photograph, it's pretty much the only one we have where he's not blurry, because he's usually sort of moving around and gesticulating and teaching. And that's a model we still try to live up to in 3091 today. And so there's been a string of people who try very hard to live up to the John Wulff legacy in teaching 3091. Toward the end of his distinguished career, he actually wrote a groundbreaking set of textbooks. He got together a bunch of collaborators and colleagues, and they wrote this 4-volume series that was called The Structure and Properties of Materials. And this book is famous because not only did he inspire 18-year-olds at MIT through his course, but he also then disseminated these books out all over the world, and he was responsible through that to introducing the field to just lots and lots of young people. And when we launched the Wulff Lecture, which incidentally we did in 1977, and the very first person to give the Wulff Lecture was indeed John Wulff himself, but we inaugurated this lecture in his honor because we admire that legacy. We admire that he took material science and engineering and he made it something accessible to young people, and he introduced them to young people who are in the midst of making career decisions and making plans about what they would study. And in fact, that's why we hold these lectures. We hope that they will be inspirational to young people who are perhaps right now thinking about what their careers are going to look like. And so if you're in that category, we offer this lecture for you. This one's for you. And indeed, today we have one of the real heroes of our field, one of the leaders who is going to give the Spring 2019 Wulff Lecture. And so it's my honor to introduce to you Professor Frances Ross. And don't clap yet, because I'm going to make you do that in a minute. But first, I'm going to embarrass her a little bit. So this is like the fun part of my job. So Professor Ross, she has a background in material science. She actually started in physics, got a bachelor's in physics, and then moved into material science for her PhD. And that, to me, is an important lesson, that material science is a field that you can come into no matter where you come from, right? Whether it's engineering or physics or science or chemistry. This is a big tent party, and all those expertise backgrounds are really welcome here. So she did that, and after her PhD, she went out and had a range of different experiences since then in industry, in academia, in national laboratories, including time first at AT&T Bell Labs, and then she was at the National Center for Electron Microscopy at Lawrence Berkeley. And most of her career was at IBM at their Watson Research Center, where she has become, to put it mildly, really famous for her pioneering work in imaging the way that crystals grow and the way that we actually make materials at the atomic level. She developed technology that really pushed the frontier on what we call in situ microscopy, so watching materials evolve. And in particular, she's credited with inventing the liquid cell for the electron microscope. And this is an amazing thing because it lets you put a liquid into a vacuum chamber and still study that liquid in the vacuum of an electron microscope. And I hope we'll hear about that a little bit today. Professor Ross is extremely highly decorated, of course, for her scientific achievements. She's received, there's a giant list. I just picked a couple. I hope I got the right ones. But we got the top award in microscopy, the Burton Medal, and the top characterization award from the Materials Research Society for innovation in materials characterization. She has an honorary doctorate from Lund University. And get ready for alphabet soup, because she is a fellow of like every three-letter society there is. APS, MRS, MSA, RMS, AVS. And if you don't know what those are, that's the American Physical Society, the Materials Research Society, the Microscopy Society of America, the Royal Microscopy Society, and the American Vacuum Society, and I think I got those right. Oh, and also AAAS. I'm not going to tell you what that one is, because I'm not sure I know. No, it's the American Association for the Advancement of Science. Okay, so this is a long introduction, but it's worth it. With the opening of MIT Nano, we're sort of entering a new era here in materials research at MIT, and MIT is making a major investment in nanoscale science and engineering, and so we have been positively thrilled in this department to have brought Dr. Ross of IBM to become Professor Ross at MIT, which we've done in the past year. We're very happy that she's here now, and she holds the Ellen Swallow Richards Chair. So, it's time for the lecture. If you have ever heard me talk about our field before, you may have heard me say, one of the favorite things that I like to say about material science is that material science is about building with atoms, and it's about learning how to get every atom in the right place inside a material. And the lecture you're going to hear today from Professor Ross is going to show you how material scientists do that in the most literal possible sense. So without further ado, it's my pleasure to welcome up here and ask for your applause for our speaker today, Professor Frances Ross, and her talk, Funny Microscope Videos.
Wow. Well, thanks for that fulsome introduction. I'm not sure if I can continue that kind of theme here. Let's see. Let's make this work. Wakey, back. Well, there we go. Wow, impressive. Well, thanks everyone for coming. I really appreciate it, and it's been a really fun and interesting journey to get to this point. I'm hoping to show you some of the things that I really enjoy about this little corner of material science, and maybe get some thoughts and inspirations about what we should do next. This is a pathway which we're traveling along. There's many more destinations along the way. So I want to give you a little flavor of how things work. It's sort of a difficult assignment, reading about Professor Wulff and how his style of teaching and lecturing was so entertaining. So we often don't give talks that are particularly entertaining. We try and impress people with how much we know. We put many equations up on the wall. But in this one, I don't think I have any equations. I want to kind of show that we see things that are surprising. We see things that are sometimes amusing in a funny way, sometimes a peculiar way, and we often see things that don't work, and sometimes the failures are informative. So all of those things make it funny. Recording videos in the microscope can be quite a funny way to do a career. So this is the kind of thing that we do. This is the movie that was on the poster. If any of you tried the QR code, this is what you would have seen. This is a catalyst. It's used to grow a silicon post. And if you look at the surface structure, you can see this liquid has a solid surface. That changes the catalytic properties. And we can see, as it operates as a catalyst, what its structure is under the growth conditions. This movie shows nanoscale bubbles. Notice the difference in the length scale of these two movies. These bubbles are a few hundred nanometers across. It's quite hard to measure bubbles of that kind of length scale unless you use a technique with a much higher resolution. And so I'll talk a little bit later about how we can see processes taking place in liquids in the microscope. And many processes depend on nucleation and growth of nanoscale bubbles, like water splitting, a lot of catalytic processes, cavitation, corrosion, many things rely on this type of physics. So why do we want to record these kinds of movies of materials in action? Well, there's a grand challenge in material science, which is our objective is to design and build materials that have particular properties. We may want something that works in an electronic device. We might want something that has certain mechanical properties, magnetic properties, whatever it is. And so in the modern era, we often turn towards nanoscience to achieve our objectives because nanoscience provides many new tools that were not accessible in the past. Shrinking materials to the nanoscale size, few tens of nanometers, often unlocks properties that you don't get in the bulk. So this is a real frontier for material science going into the nano area. But how can we actually do that? How do we, we can say, let's make a nanoscale material and make its properties match what we need. But there's a difficulty with doing that. There are generally two ways to make small objects. One of them is to assemble them by hand. This is an example from some of my colleagues at IBM, actually in the Almaden Research Lab. They made a very small magnetic bit. This functions as a memory element. It's made of 12 atoms of iron, and the spins are coded up and down. They can assemble the structure in a scanning tunneling microscope by picking up each atom, putting it into place, and then they can measure it, and they can measure the spin state and see all the different states you can get with these magnetic bits. Now, is this going to work in the real world? Probably not, because it takes many hours to make one bit, and the number of bits that you need is rather a lot more than one. So let's choose a different path. Let's do a self-assembled path. And here's a photograph during a recent rainstorm from the Nano building looking out at the dome. And you can see there are raindrops on the glass window. And those raindrops assembled themselves without us telling them what to do. Obviously, the surface tension of the water, combined with the fact that the water doesn't want to wet the glass, those two things together force the water into little hemispherical droplets. So you don't have to tell it what to do. It does that automatically. So the goal of our interests in material science is to use a technique that's as simple as this, that's fast, that's parallel, that's scalable, to make structures which in principle could be as complicated as this one. So can we use simple self-assembly to build complex structures? Well, there are some difficulties which I will illustrate with a domestic example. Now, how many of you have animals, pets at home? And how many of you are lucky enough that those pets would be cats? Yes, right. So in this picture, illustrating a typical cat behavior, you can't expect a cat to do what you want, right? So it has its own internal logic and rules that tell it what to do, and that's got nothing to do with what you would like it to do. Now, this is a typical scene recorded in our house the other day, and the cat's not doing what we want until this happens. And then you'll notice that we get assembly of the cats into this one location. So, so the goal of self-assembly is to set up a situation where the atoms do what you want them to do naturally. You don't tell each one what to do. You just make the situation so compelling that they all have to do what it happened that you wanted them to do. So this is the idea of directed self-assembly, and we aim to understand what is the mechanism of this. What is the attractive force that gets the atoms in that one place? If we can understand the physics underlying the self-assembly, we can then control it and make the types of structures that we want. All right, so I feel that in situ imaging is the key to answering this question in general, because it lets us track the pathways of the component elements. You can see the atoms as they come in. You can measure in a quantitative way what happens as you change the temperature, the pressure, the composition, whatever it might be. If you measure how external variables control the growth, at the very minimum, you generate design rules that may improve the uniformity of these random structures, but at the best, in the best outcome, we can get fundamental insights, kinetic and thermodynamic rules that will tell us how we can assemble what we want. We can see unexpected growth modes. We can learn things that maybe we didn't even think would be possible to do. So we're at a very exciting time. So I feel like we're going up this pathway like this, right? We're going left and right, but there's a general upward trend. So we're in a very exciting time for this because the in situ imaging tools are so vastly better than they were even a few years ago. The resources to analyze the data, the cameras, the resolution of the microscopes, that everything is kind of coming together in a way that allows us to really apply this type of idea of doing in situ imaging to really understand what's going on during nanostructure growth. So here's a photograph of the microscope that was used to take probably about half the movies that I'm going to show you. And so here's the electron microscope, the part of it here. The electrons are generated up here. They are focused down. They shine through the sample, which is just about in here. And then they form an image down here, which we could record on a camera or a hard drive, whatever it is. In the microscope, we put our sample, which is usually a rectangle based on silicon. It's mounted in a sample cartridge, and the middle of the sample, the little feature in the center, is thin enough for the electrons to go through. So this is transmission electron microscopy, where you shine the electrons through the sample and you record what happened to them on their way through the sample. So it's like shining light through a stained glass window. You can see what the structure of the material was based on the transmitted intensity and phase of the electrons. So this is a special microscope. You can tell from all the tin foil around here. The sample is loaded in. It can either go into the microscope where we can heat it up and flow gases, including some fairly toxic ones like arsine. So the safety team had to work pretty hard on this, but we've been working with these kinds of gases for a long while with pretty much 100% safety during our experiments. So the sample can also be put into one of these growth chambers on the side where we can add metals to it. We can calibrate the temperature. We can write patterns with a focused ion beam gun. And this part of the system is in nano on the 5th floor. So if you walk along the corridor on the 5th floor, you will see half of this system behind the glass there. So if you want to come and visit, just let me know. All right. So I feel like doing this is like playing a musical instrument, because you sit there at the console, you have the stuff, you've got the controls of the microscope, your feet are operating the tilt of the sample, you have to worry about the temperature, the pressure, what's going on with the vacuum gauges far over in the far corner. And it's like playing one of these pipe organs, right? You've got all your limbs working at the same time. And if you get all of these functions correct, you can get some data out of this thing. All right, so I want to start by showing a oh, good, a green one, much better, thanks. I want to start by showing a relatively simple experiment that in some sense is related to the water droplets that I showed you earlier. And the experiment here is that we're going to add germanium onto a clean silicon surface. So we start with a flat silicon surface that we prepare by heating up in the vacuum of the microscope. And then we add germanium atoms one at a time onto the surface at a temperature high enough that they can move around and decide where they want to stick. And essentially, we're putting the germanium atoms into an uncomfortable situation because they land on the silicon surface. They'd like to line up with the silicon atoms that are already there. But those silicon atoms are too close together. So if you have a germanium above a silicon and a germanium above its neighboring silicon, those two germanium atoms, they need a bit more space. So as they add up, they become very uncomfortable, which means their energy is high. They don't like to have a high energy. They want to find a way to relieve the strain energy that's built up. And you'll see in the movie exactly how they do that. So we're resolving the behavior in strain. Each one of these is a little mound of germanium. We're constantly adding germanium, and look at this, the small ones are disappearing, right? So the big ones are growing, the little ones are disappearing, even though more germanium is coming down onto the surface. So this to me is like economics, right? The rich ones get richer, the small ones, they fade away and they die. And in real life, who knows what this process is called? When the small ones shrink and the big ones grow. Go ahead, what do you think?
Shrinking and growing?
That's a good name for it. Okay, let's leave it at that, shrinking and growing. So this business of exchange of germanium, it dominates the evolution of the islands, right? And this was an unexpected result because you wouldn't see that if you just took the picture after the growth had taken place. You would just see that. You wouldn't realize that there were all these little unsuccessful ones that kind of blossomed and then died. So you can see it in the stills, and you can use this information to tune up the conditions to get arrays of germanium islands. So in this experiment, we set out a little defect on the surface, a little bit like a bowl of food for the cats. The germanium collects up in those spots because every site gets an equal amount of material. They all grow at the same rate. There's no coarsening. You get uniform array of islands. So we can learn something about how the things grow, and we can use that information to improve our control over the growth of the islands. Now, let me look at a slightly more complicated example where we're going to grow our nanostructure using a catalyst. And instead of just letting it grow on its own, we're going to have a catalytic site where things happen, and then nothing happens anywhere else. So all the action occurs on the catalyst. So unfortunately, in nanoscience, there's a lot of what you might call PowerPoint science, where people draw a very pretty diagram, and because the objects are too small to see, they say, oh yeah, look, there's this and there's that. But in real life, with the microscope, we can find a way to verify or more interestingly, disprove the sort of PowerPoint science that gets proposed. So this is the growth model for nanowires. You start with a silicon surface. You'll see a theme in what I talk about. Silicon is my favorite element here. So we have silicon, we put gold on top. We heat up the sample. There's a reaction between the gold and the silicon that forms droplets of gold silicon eutectic. They de-wet into little drops on the surface, just like the raindrops. And then the trick is to add more silicon. We're using disilane gas. It comes down, it cracks, it reacts very fast, very much fast on the surface of the liquid droplet compared to on the solid surface of the silicon. And so silicon is being supplied at this point. It diffuses through the gold silicon. It grows at the interface. And as the longer you wait, the further the growth proceeds. So this is PowerPoint science. This was developed before most of you were even born. This mechanism was proposed based on post-growth observation. So what happens in real life? Well, it's pretty interesting. It actually works very much like what was proposed. You can see this thing is growing. See the little features on the side? They're stationary. So you can see the growth is happening at the tip of the nanowire, not the base. And as it grows, you get a perfect prism of silicon. So every atom is in place in this column. These lines are caused by interference of the transmitted electrons. So it's like a thickness map, a contour map of the sample. So we've grown a perfect pillar of silicon, the material's adding to the growth surface. And so with this type of experiment, and I just want to show this, this is one of my favorite pictures, so it's kind of an excuse to show this one. The experiment is done by having this growth take place on a vertical wall, and then as the objects grow out away from the surface, you can see them in the perfect geometry. You can see the growth front, the shape of the droplets, the growth rate can be measured. So there's a lot of quantitative information that can be obtained from these kinds of experiments. All right, so let me show you the same experiment done in a microscope that has a higher spatial and temporal resolution. And so do you see this kind of pattern on the silicon? This is the silicon again. So now we're resolving the atomic structure of the silicon. Each one of these horizontal thin lines is one bilayer of silicon atoms, so there's 3 angstroms between those layers, and you can just about make out the individual columns of atoms in the movie. So if we play the movie, you'll see what I showed you on the, well, ignore these kind of shimmering effects, but what you can see is the growth is taking place in little jumps, right? Do you see that? It's like jump, jump, jump. It's not a continuous thing. And if I take this movie and I cut out this section and blow it up, you can see that in a bit more detail. So here's nothing happens for a while, and then suddenly the whole layer of atoms grows all at once, and then we wait, and we wait, and we wait. Come on, come on. There you go. Do you see that? Right. So what's happening? This shows us some of the fundamental physics of what's going on here. The atoms aren't adding onto the silicon piece by piece, they're going in little jumps. This is silicon. And let me show you the same experiment in gallium arsenide. So again, we have a catalytic droplet, gold gallium. You can't see it in this kind of dark field imaging mode, but you can see the structure of the gallium arsenide solid very clearly. And if you look on this movie, you can see, do you see it's actually going in back and forth? So these sheets of atoms are not forming continuously, they're actually growing rather gradually back and forth, one layer at a time, longer and longer, each one of those being 3 angstroms of extra length. All right, so I said I wouldn't show any equations, so I can explain this in a very hand-waving way to give a flavor of the type of physics that you can get from these experiments. So the silicon arrives at the catalyst at a constant rate, because there's a fixed pressure of gas in the microscope. So the silicon is being incorporated at a constant rate, and it has to make a decision. Once it gets into the catalyst, does it stay in the catalyst, or does it go and stick down onto the surface? And supposing the catalyst has a very low solubility for silicon atoms, which means that any silicon atom in the catalyst is in an uncomfortable high energy configuration. Well, those atoms, they don't want to stay there. They'll come down and they'll find the friendly silicon of the nanowire, and they'll stick onto it, and the growth will be very gradual. Every time something comes in, it goes through the catalyst, it sticks on the interface. Growth is very gradual, back and forth. On the other hand, supposing the catalyst can accommodate silicon very easily, it doesn't cost much energy to put silicon into this liquid, well, then we're going to collect up a lot of silicon in there without much penalty, and it's actually rather difficult to nucleate a step on the surface. The surface will stay flat, more and more silicon will come in, it'll get more crowded in there. Eventually, they get to a breaking point. Something nucleates a step, a critical cluster of silicon atoms forms, the step appears, and then all the extra ones, they pile onto the step edge, it shoots across, uses them all up, and then we're back to square one again. So it's a cyclic process where nothing happens, we collect up silicon, eventually a nucleus forms, and then the whole ledge is completed at once. And you can do some predictions of how the step flow should look under different circumstances. But the key message for this is actually not to do with the step flow kinetics, but with the relationship between the catalyst and the structure of the nanowire. So it's all very well to make a perfect column of silicon, but there are other ways to do that. Why do you have to go to all this trouble to make a perfect silicon structure? What's interesting is silicon with a little layer of something else inside. So silicon, germanium. You can make electronic devices like that. So what you would do, in fact, is you would grow the nanowire, you would switch off the silicon gas, you'd switch on another gas like the germanium source, and then you would expect for the germanium to start growing in the nanowire, and then you'd maybe switch back again. So you've made a quantum well out of germanium. And what we learned from the previous experiment is that this is only going to work, this PowerPoint science will only work if there is very low solubility of the second element in the catalyst. Otherwise, they just get mixed up within the catalyst, and the composition change will occur. It'll just be smeared out over many atomic layers. So we can relate the catalyst structure, its accommodation for the growth species, into the behavior of the final nanowire, so the electronic or optical properties of the nanowire that depend on the sharpness of the junction. So that's a nice little story where we say we measured something, we learned something about the physics, we used it to predict how best to grow things. So this is where it gets a little bit more interesting. Supposing we think to ourselves, let's not make a silicon germanium structure. We've done that, we've published the paper, let's move on to something else. We're going to grow silicon followed by nickel disilicide, which is an electronically important material used for electrical connections to silicon. So we'd like to make a silicon wire with a nickel disilicide slice inside it. And so what happens, in fact, is the following. I'm going to show you a movie because this is a bit hard to follow. But we add nickel and we think, OK, we're going to make a uniform layer of nickel disilicide in our nanowire. But in fact, we get this phase forming inside the droplet. And if you look at it here, it's kind of octahedral in shape. You don't have to believe me, I'll show you a better picture in a moment. This octahedron floats around, it sticks down, And now, if you continue to grow the nanowire, this little thing is left embedded. So it's like an ice cube floating on the surface of a drink just here. And as you just keep filling it up, it eventually gets stuck in and buried. So instead of forming a layer of material, we formed a little block of material inside the nanowire. So here's the PowerPoint diagram of how that works. Instead of making a sheet, we get the new phase in the liquid. It floats around, it sticks, and then it can be embedded. So who would have thought of this? This is just so interesting and weird that we had to try it a few times before we believed what we were seeing. But this is, in fact, somewhat reproducible. And I'll show you in this movie how the thing can stick down and get stuck in a perfect crystallographic orientation. Do you see that it's actually rotating? It started out at a higher angle. Maybe I'll show that again if I can. Okay, do you see it's got quite an angle to it? There's some steps in here. And then as time proceeds, it jumps down into place. The silicon here is moving out of the way. This thing isn't giving up any ground, but these silicon atoms are diffusing away until you get the perfect alignment between the two. So you can have a floating phase that comes down and sticks into alignment. And then as you continue the experiment, come on, do it. Here, this is a different wire, obviously. You can see it getting buried inside the nanowire. Okay, so that's truly a quantum dot. The other one was a sheet. This is actually a little octahedral thing. So the message from that is that it's quite fun. You see something that you didn't even imagine would be possible. And then, of course, once you see it, you write a fairly dry scientific paper that says, well, of course, this is what we expect to see. And here's the proof. And here's some mathematics to make it sound more convincing. But really, it's often the case with these microscopy experiments that you see something that's not what you expected. And it's even more frequently the case that you see something that didn't work at all. And you think, well, what am I going to do? Here's one where the vacuum level in the microscope is not good enough to do the experiments. So instead of growing the nanowire, we're growing this cruddy layer around the surface. And it took us some while to figure out what was going on here, because this is not made of carbon. You'd think things get dirty, they're covered in carbon. But what's happening here is that we have water vapor or oxygen contamination in the vacuum of the microscope. And the electron beam combined with the silicon source and the water vapor creates silicon oxide, which coats the surface and kind of prevents anything from happening. So you sit here and you sit here for a long time and nothing happens. So anyway, so we have to really control the environment in the microscope for these things to work. We often get weird growth, like when there's the arrival pathways for the atoms are compromised. This is because of contamination on the surface. You get these little beach umbrella kind of structures. And this is a case where the wire changes direction. So the wire's growing up, it starts to make a kink, and eventually it makes actually a U-bend and goes back down again. So that's pretty interesting, but not what you want. And here's one where we were really a little disappointed at the start. But this actually, so look at what's happening to the little nanowire. You remember that coarsening process I showed you where the small things disappear and the big ones grow? So the same thing can happen even when each thing is on the top of its own little island, its own little pillar. So coarsening, Ostwald ripening, is making this small object diffuse away. The gold's actually diffusing down the wire and up to some of the neighboring wires. This wire has died. It can no longer grow. Its catalyst is gone. So you think, well, that's too bad. But in fact, this analysis ended up being the paper we wrote that had the most citations out of anything I've ever published. So that just goes to show something. I'm not quite sure what. Anyway, so the last thing I'll show with these gas phase reactions is that I showed little reactions taking place in the droplet on top of a nanowire, and you can actually quantify those in quite an interesting way by removing the nanowire and just having a little droplet. So here's a droplet of gold silicon liquid. We add more and more silicon. We see the nucleation of the silicon, and you can measure the growth of that. You can combine many experiments at different temperatures, pressures, and diameters, and come up with a model that gives you otherwise unmeasurable parameters like the supersaturation required to nucleate, you know, what the trigger has to be to cause a nucleation event. So this is an example where quantitative data can come out of these experiments. And then another thing we can often see is things that are rather fast and would be difficult to see otherwise. So look at all these nucleation events. It's a bit jumpy. But we have, if you imagine here, the whole thing is in the field of view. Every phenomenon that's going to happen during this sequence of phase transformations has to happen within the field of view. So without doing these in a nanoparticle, it's always the case that the interesting thing happened off screen. And then you saw it after it happened, but here they have to happen within. And then the last one I'll show you is a sort of dynamic one. It's a bit hard to see. See this little object? We call these rattlers because there's a solid object inside a liquid and it just kind of shaking around by thermal motion. And so it would be entertaining to do some analysis on these, but I'm not really sure what we would learn. Still, it's a fun kind of a phenomenon to look at. So you can see that doing gas phase reactions is a useful way to understand the physics of materials growth and to see phase transformations, unexpected phenomena, pathways of atoms to get to their final configuration, and to use that to design particles or nanostructures with specific properties. So can we translate those ideas into reactions that don't just take place in the gas phase? In other words, we want to have a liquid medium for our growth instead of just supplying vapor, which is much easier to do in the microscope. So how do you put something like water in an electron microscope, which has to have a vacuum within the column? And the reason we need a vacuum is because when the electrons are generated at the top, you don't really want them to hit anything else on their way down except for the sample. So you need actually a very good vacuum above and below the sample. So the answer to this engineering question was actually developed back in the 40s when microscopes were first being developed. Röske himself, who won the Nobel Prize for developing the electron microscopy, he postulated a little box of water with a thin window above and below, and you shine the electrons through the whole stack. And unfortunately, they didn't have the right materials to make that work in an engineering way. So now we have microfabrication. We have silicon nitride, which is an amorphous, very strong material that can make these windows. We have machining techniques that can make our little sample holders, and we can jam all these things in and end up with something that maybe looks like this. This is a typical example. There's water in here. There's a silicon chip beneath with a small window with a silicon nitride covering. There's another chip above that also has some ways to let the liquid in and out, so you could flow it. It's not shown here, but you could flow liquid through here. And then you have the electron beam in the microscope. It passes through the top window, through maybe 200 nanometers of water. It may pass through an electrode on the bottom window, and then there's the bottom window, and then back out into the vacuum. So you don't get fabulous resolution through these cells, but you can at least see things happening with a good combination of time and space resolution. And I want to point this out because obviously there's many ways of looking at things happening in water, like using a light microscope, but there is no technique that gives you decent spatial resolution and decent temporal resolution. Light microscopes give you resolution in the hundreds of nanometers, maybe a little bit lower with fancy techniques. Scanning probe techniques in water give you fabulous resolution, but it's really slow. It's maybe a minute to get each scan, so you can't see stuff happening quickly. So TEM has this little niche it can fill. So that's a lot of talking, but here's an example of an early cell that was glued by hand. So we ended up with a little paintbrush that we cut all the bristles off except for one. And then we were using this epoxy, two-part epoxy that you mix up and you have a few minutes before it goes hard. And then you paint it around here with the paintbrush. You squeeze it together to get the windows close together. And then you fill it with liquid, and then you stick some lids on the top. So the success rate was pretty low. So this had to be, you need a lot of patience and not drink too much coffee when you're going to assemble this. But nowadays, of course, it's much easier. You buy the stuff commercially, it gets put together, it's squeezed with an O-ring, and the success rate maybe is 1 in 2. Which is really good. So now we can get these fancy electrode patterns. You can flow the liquid, you can mix the liquid, you can put an element in there to heat it up, and you can do a lot of different experiments. I want to show you a couple of electrochemical experiments, just because that's where I find the most interest to come from these types of liquid cell projects. So this is a movie showing what happens when copper is plated onto a gold electrode. It's more or less real time. It's about a micron across. And here's the copper clusters that are nucleating, growing, coalescing, and you can track the behavior of each one. And at the same time, you have the electrochemical data that goes with it. So we're driving this copper deposition by putting copper sulfate in solution and then putting a voltage between the liquid and the electrode, and then the copper ions land on the surface and get discharged, and you grow the copper. So who knows what IBM wanted to do with copper plating a few years ago. This is what's used for all the interconnects in the electronics. So the interest was, how does it nucleate? Can we improve the nucleation? How thin can the layer be before it becomes continuous? And so we thought, we can answer these questions, we'll tell them what to do. But in fact, all we ended up doing was some basic physics, and the engineers found the correct solutions, additives, and processes to make the things they needed. Anyway, so what happens when you grow a little bit more material a little bit faster? This is now the edge of the electrode. So before we were looking in this kind of area at stuff growing on the surface, and now we're going to grow so much stuff that we fill up that space, and now the only way to grow is outwards. Right? So does that all make sense, that geometry? And so what you can see when this happens is the growth front is kind of flat, and then it becomes dendritic. So this is the process of recharging a battery. This is what happens in, say, a lead-acid battery when you recharge it. In some lithium batteries, you redeposit the metal back onto the electrode. And then as you discharge the battery, you would dissolve all this stuff away back into solution. So there's a great deal of interest in controlling the morphology of this growth front so that you avoid stuff like this. And this is very common in zinc-based batteries. And these kinds of dendritic structures can really compromise the performance of the battery. So we can, in fact, do some fairly detailed analysis of what goes on during this process. We can see how the growth front morphology depends on the rate at which we deposit the material. And we can show, in fact, that if you recharge the battery very slowly, you tend to get a flat surface. And if you recharge it very quickly, you will get this kind of rough surface. And that's what people know happens. But the interesting thing is that by tracking the behavior of each little bump from the initial to the final state, you can prove that the tall dendrites, they grow from bumps that form spontaneously. There's no way to avoid this happening, for example, by polishing the surface of the electrode or by treating it with some chemical that makes it very flat. So you need instead to control the roughness by some other means. So here's one quick experiment where we test the behavior of deposition under different chemical conditions. And in fact, you can sort of improve things instead of getting a lot of roughness. Here we have a kind of a lesser roughness, so it sort of works. But the next set of movies is a different way of doing that, which provided me with a lot of amusement during these experiments. So the idea is that you don't want to grow too quickly because that causes roughness. So you give a little pulse of growth, and then you wait for all the concentrations to smooth out. And so then when you grow another pulse, maybe it will be smoother the next time. So this is the sort of physics behind it. We're pulsing, we're doing a growth for a few seconds or 1 second, then we're waiting for a few seconds. Here's the concentration as a calculation of what it should be doing. And under these conditions, we hope that the growth will be flatter. So this is how it works in real life. We're doing this pulsing experiment. You can see every pulse, we get a little bit of material growing. And you see it's actually quite smooth. So we've now grown just as much material as I shown in that previous movie with the spikes, but it's very smooth. So we said, great. So the next step is you grow, and then you remove all the little spikes. That should work even better, right? So you take 2 steps forwards, 1 step back. You should knock off each little asperity, and you should get an even flatter surface. So look carefully at this movie. Of what's called pulse reverse plating. We're adding material, then we're actually subtracting it. And in fact, it's doing quite the opposite. So this is economics at work yet again. See this guy? So so this is one of my favorite movies because it really seems to show that however you try to keep things, you know, equitable, smooth, it just, yeah, nature finds a way around it. Okay, so the last thing I'll show you is just some other applications of liquid cell microscopy. You can look at corrosion. This is what 2% of the GDP is going on in here. You can see this aluminium grain is getting corroded, see the little pits forming. And we can follow these are slow experiments. These maybe you do it and then you wait for a day, you put the metal in salt water, you leave it alone for a day and you look at it again. This kind of thing happens. Here's the addition of material, the opposite process. We start with a liquid that contains metal ions. Gold ions in this case. We put the electron beam onto a point and we watch what happens. The electron beam is reducing the metal ions locally, and all those reduced metal ions are coalescing into a polycrystalline object, let's call it, which has this sort of dendritic structure. So this has some kind of limited application. You can write patterns, so we always end up writing the names of the collaborating institutions. That's what you do when you have a way to write things in any kind of science, I think. And this one I liked because this is still in the liquid from which it formed, and then a bubble formed and passed across the field of view and left this wreckage behind, which kind of blew them away. So I like that, right? Okay, so that's kind of what I want to say about where we are now. And I've picked these examples because they illustrate some of the things I like about this in situ technique. You can get a continuous view of a process, and that helps you to probe the physics that's going on. You can use that information to create structures that you didn't imagine were possible before. You can see how things behave under real conditions instead of after you cool them down and take them out and take a picture of them. You can get detailed kinetics that can be calibrated. You can catch these transient states like rotating particles or the sequence with which things nucleate. And you can get all of that information not just in gas phase but in liquid phase experiments. So I want to finish with a few slides on where we're going to go next. You know, we're at this point where the equipment is developing and improving every year, and how can we use that to get to go a little bit further along the same pathway? So I'm going to just briefly mention three different things: how we can improve the design of the sample holder, to increase the range of processes that you can look at, how you can use the new capabilities of microscopes to see materials that are not possible to image here, and how we can quantify things better, both in terms of modeling and in terms of you know, analysis of the data. So the first thing I'd like to talk about is the use of microfabrication in the sample and in the sample holder. So we very often use microfabricated samples. So they have little cantilevers, they have things that can be heated up, they have geometry that we can design and fabricate. This one shows two cantilevers next to each other. These things are designed such that there's a constriction. So you pass a pretty small current, like some milliwatts, through this thing. It's silicon, so it's doped to conduct enough electricity for this to work. So these points get really hot. Because of Joule heating. The heat can escape on this side, which is joined to the substrate, but the heat here cannot escape, so the sample gets very hot for very little input power, and that causes less drift, which is really good for the microscope. So if we make a cantilever and we make another one, we can then make the nanowire grow as a bridge between the two, as in this little diagram. And the reason we want to do that is because we can grow a single structure, and then we can cool it down and measure the electrical properties. Maybe what the transport, the current voltage characteristic is for that individual object that we designed and built in the microscope. So these experiments, there's a gap of 3 microns. That's about the limit of this lithography for these particular devices. So it takes a long time. It takes several hours. So we're not going to see the whole thing, but here's the final stage of the nanowire growing across and attaching to the other side. And what's going on here is that the catalyst, the gold in the catalyst, as soon as it reaches this point, it diffuses away, and the silicon continues to grow until you get a perfect bridge. Should we look at that again? Is it going to go? Oh, never mind. Okay, so I have some more fun ones to do. So let's say we grew that thing almost to the end. We didn't make contact. We stopped there, and then we applied a voltage between the nanowire and the contact. And you can imagine this did not happen by chance. Well, it did happen by chance the first time, and then after that we got interested in how this would work. So here's the nanowire, here's the contact is just off the field of view, and we're going to apply up to 100 volts between here and here, and it's only a few hundred nanometers, so that's a pretty powerful electric field. So this is what happens when you put a voltage on a liquid that's conducting, and you can see it's getting stretched. So this is what happens in field emission off a liquid metal source, and the last frame of this movie is deleted because the whole thing blew up. You can see it got very long, and then something happened and it died. Now, if you apply the field at an angle, you can pull the liquid drop over to one side, and that has a really interesting effect on the growth rate on the one side versus the other side. So look at how this nanowire is responding to its liquid being pulled over. It keeps growing with the same crystal structure. The growth plane is always crystallographically the same, but it's actually made a kink. It's made a curve all the way around. And so this is possibly useful for some devices to study low-temperature physics, but this is something where we always say, oh, yeah, somebody else can use it for something. We're just watching it actually grow. So maybe, yeah, so this next example is about quantification. So normally, we find that we do an experiment, and then we don't understand it, and we go and talk to our colleagues who specialize in modeling, and we say, what was it that we just saw? Can you explain it to us? And so this is a frame from one of the models that predicts how, that explains how nanowires grow. So this slide shows something that happened the opposite way around. Our colleagues had their model, they were trying different things, and they were very interested in what happens when the droplet is the wrong size for the diameter of the nanowire. How does it actually grow? Does it just shrink and make a narrower nanowire, or does it do something else? And their model showed this. And they sent us this movie, and they said, this is really fun. Can you make that happen? And we thought, well, you know, how are we ever going to make that happen? But then we looked back. Somebody remembered that something had happened, and we have a problem with data. We have thousands of tapes, cassette tapes with data on, but somebody remembered, oh, over there's a tape, and it has this thing. And here's the corner of we were looking at something down here. But up in the corner, there was this thing, and the human memory showed that we could track it down. Look at that, it's doing the exact same thing, except in 3 dimensions. There's 3 little facets on the end. So how can you do that without having the same person who did the experiment still there, you know, 5 years later when this thing happens? Anyway, so the last thing I'll show you is what's going to happen next in MIT. We have, of course, a common interest with everyone else in 2D materials. They are so fabulous. There are thousands of them. They all have interesting materials properties. But every 2D material lives in the 3-dimensional world. How do you connect something that's only one or a few sheets of atoms thick to the bulk, to the rest of the universe? And so we're interested in how the concepts of epitaxy and crystal growth and nucleation, how do they apply when the thing you're growing on is only one sheet of atoms thick? So this is the best we can do so far. In the background is graphene. It's 3 layers thick. You can't even see it because the microscope lacks the resolution. On the top of the graphene, we grew some gold triangles. We're going to heat up those gold triangles to try and make them do something interesting. And somewhat to our surprise, they did do something very interesting. They're actually skating along the surface. So each one of them is sort of jiggling back and forth. And if you look closely at this one, you'll see that it changes, it rotated, right? So these are not very well stuck down onto the surface. So we have a fabulous opportunity to look at how one crystal grows when it's next to another one with which it shares very little in common. The bonding between the atoms is different. The spacing, the geometry could be completely different. And yet each crystal wants to do the lowest energy thing, and we can investigate those. So in order to do this, to get pictures like this, which is post-growth imaging, in the microscope so that we get a movie like this, but with this kind of quality. We are developing a new microscope that will go in nano, and it will have atomic resolution, aberration correction. It will have analytical techniques to tell which atom is which. It'll have very fast time resolution, and it will have the ability to image 2D materials without damaging them by using low voltage. So this is going to take a while to come, but I'm very excited by the possibilities. So I'd like to conclude by saying that I think we're in a fun moment in time for this type of material science. We have a desperate need for new materials, and especially for new ways to grow them using concepts of self-assembly. And we have the opportunity to use the developments in imaging tools that are just barreling along, driven by people who want to do straight imaging and analysis of materials. If we combine these two things together, we can really start to use this type of instrument to understand the physics of this type of growth, to then use it to control and make more complex structures in the future. So the last thing I want to do is acknowledge everyone I've worked with in this, and especially the technical support. Mark and Art at IBM, who built the equipment, who made it run, who made the changes when we would say, now we want to deposit aluminium. Can you make that happen? And they would just make it happen. Can we change the camera? Can we modify this or that? And so this is really the center of it all, and then all the students we've worked with and the advisors who have been kind enough to loan us their students to do the experiments. All right, thanks for your attention.
All right. I will open the floor for questions for the speaker, and as is our tradition here at the Wulff Lecture, we're going to give preference to students. So feel free to self-identify as a student, and I'll give you priority. You're a student, and I know it, so go ahead. Here.
So this morning we had a great microscopy success announcement, albeit at a very different scale, with imaging the first black hole, and fortunately it sort of matched the relativity predictions. But whereas here you've shown us examples of things that didn't match PowerPoint science. So my question is, have you ever reported any of this data and have had pushback from PowerPoint scientists, and how has that panned out?
I feel like it's hard to argue with an actual movie of something happening. And that's where we do have let's say, an advantage in being convincing about what's going on. So we can say, look, every frame of this movie, you can see it all happening. And even with a before and after picture, there's still some question. So as you saw in many of those, there's still ambiguity. The resolution doesn't show every atom. The time resolution is maybe 30 images a second or 400 images a second. We want to go better. And the more data, the better the resolution in time and space, the more compelling you can be. But generally, just showing people images is a good way to sort of, convince them that something happens. Yeah.
Other questions, please.
How many years of work did you just show?
Well, I showed some highlights that were spread around. So the oldest thing I showed was probably 12 years ago. Some of the liquid cell movies. Everything else, I think, has been before that, and most of this stuff was in the last few years. So, yeah, yes. So it goes, and then there's a burst of things and then you move on to something else. So, like with all science, it comes and goes in waves.
Wait a minute now, are you a student?
A student.
Oh, no, I'm just kidding. Go ahead, please.
Would any of this help with astronomy?
We're using some of the same cameras that were developed by astronomers because they have the same problem. Very faint objects, not much light gets through them. So the camera has to be very sensitive. And so with many of these samples, every electron that you use to make the image causes some damage to the sample. So you want to make the image with the least number of electrons. So we use the same cameras, and we have, even the astronomers, they use cameras where they measure the time that each photon hits. And then you can do things like correct the shimmering in the atmosphere. You can kind of correct that out. So a lot of the idea that you're recording difficult data and trying to do quantitative measurements, that's in common with the astronomy guys, yeah. You know, I wanted to be an astronomer when I was at college after 1 year. And then we had a summer experience I was in the UK, and I went to one of the astronomy centers and I worked, and it was all computer analysis of data. No actual experiment, just sitting with the computer. And then at that time, the UK was reducing its funding in astronomy, and those people went to work for the DMV. So I thought, no, I'm not going to do this. That's not worth it. So then I went more towards materials.
That's truly inspiring.
Yes.
Okay. Yeah. I think there was another question in the middle here somewhere. Did I see a hand? Or anywhere? No restrictions here. Any other questions? Yeah, please.
What's the high voltage and the low voltage that you mentioned?
Much of that stuff was done using electrons that were accelerated to 300,000 volts. And that's a typical material science voltage that gives some damage to the sample, but also gives good resolution. So it's a compromise. And then if you go down by a factor of 10 to 30 keV, you don't damage the sample nearly as much. And in the past, that also meant you had very poor images because the wavelength is longer. But now we can correct for the distortions in the lenses at low voltages, so we can get good images at low voltage. So that's been a real game changer in the whole microscopy field. And it would be good to go lower, but 30 again is a good compromise between the loss of performance and the reduction in the damage to the sample. Yeah. One more there. Go ahead.
So, how would you think, like, pushing the temporal resolution for imaging, especially for the growth kinetics? Like, do you think going to a certain frame rate, below a certain, or sorry, above a certain frame rate would actually help?
Yeah, I like this question because there's no answer to it, right? So what we'd say is, supposing you could record something faster, then it would also mean that you could observe a phenomenon that maybe gets faster with temperature. You could go up higher in temperature. So you're looking at some physics over a broader range of temperatures, and therefore you're getting a better insight into what's going on. So there's no limit where you say, if we achieve this, we're good, and if we don't, then it's useless. You have a sort of continuous improvement. You run into a limit because every image needs a certain number of electrons to form it. And so the faster the frame rate, the higher the dose to the sample. So especially for liquid cell experiments, where there's a lot more damage, you have to say, what's the minimum? How fast could I go to keep below this dose for this time? And every experiment then becomes a big compromise. So in fact, you want the ugliest image that still has the information that you want. That's where we get pushback from journals, actually. Why are your movies so awful? They're just fuzzy blobs. There's this black blob and it's growing. And you say, I'm minimizing the dose. It's like biologists who have to use low-dose imaging. But for sure, if you want to go to nanosecond resolution, you would have to use a high dose. You could maybe use a repeating phenomenon and do some kind of stroboscopic things. So there are ways to go to high speed phenomena, but only under certain conditions. Yeah.
All right. Well, so again, I want to thank you all for joining us today. Thank you on behalf of the department.
Yeah.
At this point, I think we'll adjourn, and I would invite you to join us outside the store, where I'm led to believe that there's a whole lot of food for you. So we would like you to hang around, and please come ask more questions and continue this discussion. Before we do that, though, I'd like to ask for one more round of applause for Professor Ross for an amazing lecture.